Hi everyone. So we have been discussing a lot of mathematical and stochastic modeling with some applications. However, there is no better way to bring these techniques to life than to apply them to some real problems that we can connect with. Coronavirus has been causing a lot of suffering, public health emergencies, anxiety and economic challenges. So it connects all of us, and let's discuss how mathematical modeling is used to understand and contain the spread of such infectious diseases. Infectious diseases spread via infected people infecting other people, so it is like a reproduction process. The agent could be a virus, bacteria, etc., which for coronavirus is a virus. The clue is in the name. The role of mathematical modeling is obvious. It can help estimate the number of infectives over time. You would frequently see in social media people using exponential curve to describe the spread of the disease, but this isn't how the actual mathematical modeling is done in practice. The increase in the number of infectives in the initial stages of the spread looks exponential, so that's why people rush to fit exponential curve. Curve fitting might be good for some applications, scaremongering for example, but one needs to model the essential dynamics of the infectious disease process in order to gain insights into the drivers of the spread and inform the containment strategies. The questions that one can answer with mathematics could be: will the disease become an epidemic, which essentially means large spike in the number of cases over a short period of time? Will it become extinct or endemic, which means whether it disappears or stays with us? Once we have a reasonable mathematical model of the spread, then we can evaluate the relative effectiveness of various containment strategies. Mathematical models don't require a lot of data and hence can be quickly put to use, and time is of the essence when dealing with emergencies. The list of uses of mathematics is boundless. For example, at later stages when one has a vaccine, then models can also help determine the optimal vaccination strategy to achieve herd immunity, for example. You're not supposed to capture all the details in a mathematical model, just the essentials. Infectious diseases involve microscopic processes, the little creatures such as virus and bacteria and their actions, and macroscopic variables such as impact on communities. So capturing everything is not going to give you a tractable model, so the principle of parsimony is the key. The classic framework for the modeling of the infectious diseases is the so-called compartmental modeling approach. So you divide the population into sections or classes, say susceptibles. These are the people who haven't been infected yet, the infectives, and the removed, which is the class that contains the recovered and the dead. One can call the removed class the happily ever after class, depending on one's religious views. This compartmental framework can be modeled at different levels of complexity. One can use deterministic maths, so this would mean differential equations describing the flows between the compartments. This is the classic approach, by the way. However, this approach works well when the disease has spread slightly so that we can apply averages, but it doesn't work at the beginning and one has to use stochastic processes. These involve the same concepts we have encountered multiple times before, like the infinitesimal generators, probability density, and Kolmogorov equations, but applying these concepts here bring them to life and they suddenly become more relatable. And to make these models even more realistic, one can combine networks and the stochastic calculus. So you can imagine people as nodes of the network and the context between them as the edges. So you get even more realistic description of the process, but the maths get slightly complicated. So in this video, we are going to cover the deterministic models. This helps introduce the terminology used in the modeling of the infectious diseases, and we will then cover the stochastic modeling in the next couple of videos depending on the interest. We will encourage you to apply the models to the data of the communities and countries that you follow, and use these models to determine what alternative strategies can be employed to contain the spread and help plan for the care of the people, and compare and contrast the effectiveness of the strategies used by different countries. By the way, we are only focusing on mathematical modeling for now because, as mentioned before, they are easy to develop and analyze. One can also use statistical type approaches, but they are data hungry and reliable data is going to be a challenge. This is almost always the case in real life situations, so probably not a great excuse, and let us know if there's any relevant models one can fit. Another use of statistics and machine learning is in helping diagnose the infectives on a large scale, say using facial recognitions and temperature scanning, and maybe potentially determine the disease life cycle patterns and why is it more severe in some cases than others. But this requires a lot of data which we don't have access to at the minute, so these things will have to wait. Right, so let's introduce the compartmental framework. At the beginning, you have the population of susceptibles. So these are people who can get the infection, and this is one compartment. One of the individual gets infected and then infects other people, and the number of infectives grows. So this is our second compartment. I for infective. Some of the infectives recover or die, so this compartment grows and we label it R for removed, though it includes both people who have recovered with immunity to the virus or have died. This basic framework is called SEIR. So the flow is from susceptibles to infectives to removed. This framework is for diseases where upon recovery one develops long-term immunity to the disease. Generally, this is the case for virus-based infectious diseases. For diseases caused by bacteria, one generally doesn't develop immunity, so the SIS framework is used for the modeling of these diseases. So the flow is from susceptibles to infectives and then back to susceptibles. Many variations are possible within the compartmental framework. For example, for some diseases, one only gets short-term immunity, so there would be an additional flow from R to S, leading to the SIRS framework. Or it could be that there is no recovery and you will then have the SI framework with just two compartments. By the way, this same framework can also be used to model the spread of fake news. So infected would then be the people who have the fake news and are spreading it, and recovered are then the enlightened. So many variations are possible, but one has to base the choice on how the dynamics of the infection works. Generally, the way the infectious disease is spread is you get the agent, virus or bacteria via contact with an infective. The virus will try to overcome the immune system and it will take some time, and at some point you will become infectious. You may or may not have the symptoms yet, but you can spread the disease to others, though the infectivity might be lower than when you start showing symptoms. And as you recover, you will become non-infective and then start living the happily ever after. So you can add another compartment of the exposed. So the SIR will then become SEIR and SIS will become SEIS and so on. So we understand the compartmental framework, and let's see how one can model the flows between the compartments. Here we are going to be using the deterministic calculus. So the flows will take the form of differential equations. Let's start with the flow from S to I. Individuals flows from S to I when infectives mix with susceptibles. So it is like a chemical reaction and the law of mass action applies. Now if there are n susceptibles and m infectives, then the number of interaction will be of the scale of S times I. These will vary with time as the individuals flow between the compartments. We can save some space by capturing dependence on T via subscript. So the rate of change from S to I, which is the change in the number of susceptibles with respect to time, will be proportional to S times I. Let's represent this rate by beta. This beta captures both the contact rate between the individuals and the probability of transmission of the virus, so we are talking broad averages here. Similarly, let's represent the rate of flow from I to R by gamma. So we can write the rate of change of I as the inflow from S minus the outflows to the recovery or dead compartment. And the rate of change of R then is just equal to the inflows from the infectives compartment. The sum of these three compartments give us the total population. The total population can change over time due to vital population dynamics, births and deaths, but since we are interested in modeling epidemics, which only last for a few months, we can ignore the natural births and deaths and assume n is constant over time, but it's easy to add the births and deaths if one likes. By the way, one most commonly sees these differential equations in terms of population density instead of the size of the compartments. So, for example, you will have division by n on the right hand side of the first differential, but it doesn't make much difference to the analysis as the total population is constant, so it is just a scaling issue, but better be aware. Other possible variations make the real difference by enriching the framework. For example, one can make the infectivity a function of the time since infection. So now we can get more realistic model of the actual infection process. So this equation is essentially taking the infected population along with the time since they got infected, which is captured by t minus tau. Remember, the derivative of S with respect to t captures the flows to the infected department, and then multiplying by the infectivity, beta, which now is a function of time since infection. And the simpler version we are considering here, we assume all currently infected people have the same infectivity, beta, irrespective of time since infection. And for another variation, one would expect that the contact rate, the infectivity rate, and the recovery rate could be different for different strata, such as different age groups. So one can introduce multiple strata into the framework, but one then has to know how to solve the system, which may not be as simple, so one might have to resort to numerical methods. Right, so let's see how one can solve this system in the simpler case, and we will see these models provide insights that are not very obvious. So that's the reason behind their popularity. This is what mathematics is for in it. We can solve this SEIR system, but let's consider the equivalent SIS first, which is easier because we only have two compartments, so we have two differential equations. The recovered flow back into S. Now n, which is the total population, is fixed, so we need to solve for either S or I. Let's go for I. So we substitute n minus I for S. Let's remove the brackets and combine the I terms. We just have to solve for I now, and then we know S plus I equals n, which is a constant, so we can then determine S easily. Now this differential equation is the famous Bernoulli equation. It's not a linear equation, but one can easily linearize it by considering the following transformation. We need the derivative of I, which is easy to calculate. Now let's substitute these into the Bernoulli equation. And now if we multiply by y squared, then the equation turns into a linear equation. And we can rearrange the terms to write it in the familiar form. And it's easy to see that this equation can be solved via the integrating factor method. The integrating factor is the exponential of the integral of the coefficient of y. So multiplying through by the integrating factor we get. Now we can write the left hand side as the derivative of the product of the two terms. And we can now integrate from 0 to t. So the derivative and integral on the left hand side cancel. And we can easily evaluate the integral on the right hand side but the result will differ depending on whether the term in the exponent is 0. If it is not equal to 0, then we know the integral of exponential will produce this expression, and we can then evaluate these expressions at the upper and lower limits. Notice exponential of 0 gives 1. On the other hand, if the term in the exponent equals 0, then the exponential term will become 1, and the integral from 0 to t will produce this result. Now we introduce this y to linearize the equation. Our object of interest is I, so let's reverse the transformation now. So let's substitute 1 divided by I for y, and we can rearrange to isolate it on the left hand side, and we can do the same to the other solution. We substitute 1 divided by I for y, and then isolate it on the left hand side. So given the parameters beta and gamma and the population size, we have an equation that tells us the number of infectives over time, and by knowing I, we know S, so we know everything there is to know. We can plot S and I over time, and we will be able to tell the number of cases, whether the disease is going to become epidemic, etc. Most useful for comparison with more general system is to plot I versus S. So it's going to be a straight downward sloping line in this case, but this diagram is more important when one moves to more complex models. Now let's see what happens as t goes to infinity. The behavior of the first equation is trivial. It goes to 0. For the second, shift the exponential term downstairs so that it's easy to take the limit. We again have two branches. If the condition is less than 0, then the limit goes to 0, so it's the same fate as the previous case. And if it is greater than 0, then as t goes to infinity, the exponential terms will go to 0, which we can simplify and simplify further. So the condition is the key, and we can rearrange the inequality to get memorable result. So we can interpret n times beta over gamma as the threshold for whether the disease will become epidemic. This ratio is called reproduction number, or reproduction ratio sometimes, and is a very important concept in the epidemics. This reproduction number has a very easy interpretation. We know n times beta really means the average number of people infected by one infective per unit time. And remember, the gamma represents the rate of flow from the infective compartment. So you can see 1 divided by gamma really represents the average time an infective spends in the infectious compartment. So the reproduction number is the number of secondary infection produced by one primary infective. And if one infective produces more than one infective, then we have epidemic. But if it's less than 1, then we don't have epidemic. And this is a very important result that generalizes. Now this was for the SIS. Let's move to the slightly complicated SIR. We have 3 equations, so we can reduce it to 2 now, which is 1 more than the situation in the previous case. We can then solve for the 2 variables using several alternative methods. But let's try a simple method that would give us all we need to know, so no point in complicating things. Let's start with the first equation. Let's separate s on the left hand side. Now the left hand side is just the differential of log of s, so we can easily integrate from 0 to t, so we get. Now we need to calculate this integral of I, which we can easily determine by considering the sum of the first 2 differential equations, which we can write in differential form, and then integrate from 0 to t. And we know the sum of S0 and I0 is the total population, so we can substitute n for their sum. We are interested in the integral of I, so we isolate it on the left hand side, and then substitute this expression in the main equation. which we can rearrange to get variables on the left hand side and constants on the right hand side. So we have the equation which we can use to generate the scatter plot of S and I. Say plot the solution in the SI plane, say I on the horizontal axis and S on the vertical axis. Now, as before, there are two things we would like to know: how the infectious population changes over time and what is the fate of the different compartments. Studying the behavior of the infectious population is easy. Let's isolate IT on the left hand side. Now, if you look at the differential equation of I, it's easy to see what happens to I over time if one factors out I. So if the terms in the brackets is greater than 0, then the number of infectives will increase, and if it's less than 0, then the number of infectives will decrease. Notice beta and gamma are constant, but ST changes over time as the individuals get infected. So we can deduce that the I will attain maximum when the derivative is equal to 0. So if we substitute this for S, we get the maximum number of infectives, which we can rearrange. So the key to the growth in infectives is again when beta over gamma times S is greater than 1, which is more or less the reproduction number we saw before. Now let's deduce the fate of the disease. So we let t go to infinity. So we just have to replace t in the subscript by infinity. Now from the sum of the S and I differential equations, we see the sum is a decreasing function, and since the sum of S and I is non-negative, because the population can't become negative, right, it has a limiting value, meaning its derivative will go to 0, and we thus deduce that I infinity goes to 0 eventually. It might increase initially depending on the reproduction number, but it ultimately goes to 0. So we can set I infinity to 0 and shift the terms, which we can rearrange to get the so-called final size equation. So it gives the relationship between the initial population and the final population of the susceptibles. This S0 divided by S infinity in terms of the two terms on the right hand side, the first of which is the reproduction number and the second is the attack ratio, because it just represents the proportion of the population that will get infected at some point. Now the right hand side of the final size equation is a finite number, so we deduce that the left hand side must also be finite, which means S infinity is not 0, which means no matter what happens, there will be some susceptibles who will never get infected. Let's hope it's you and I. It's a very important result that's not obvious in the beginning, and you can see mathematics can provide very insightful results. This result again applies quite generally across models. So we saw that the reproduction number is the key. So we look forward to seeing your estimate of the reproduction number for different countries, and we look forward to seeing you in the next video when we discuss stochastic version of these models.